Thanks.
Thank you, Rich, for being with us today. Richard is going to present touch, interaction, and presence in telerobotics with some practical experience from the field. Rich, over to you.
Oh, thank you very much. So hi, I'm Rich Walker. I'm the Managing Director at Shadow Robot Company. As some of you will know, we've been building hands for robots for over 20 years, and we've got a lot of experience in touch sensors that work and don't work, and sensing methods that are interesting and practical, and sensing methods that are uninteresting and impractical, and a full spectrum in between. So today I'm just going to run through a little bit of our recent work, and hopefully that will give you a feeling for what we've been doing and some ideas about places where a sensor touch can be deployed usefully and what might be necessary to make that happen. So we've been doing this for a long time. There's about 40 something of us now. We're officially a company in hyper growth mode. We've grown over 20% every year for the last 5 or 6 years. So if you're looking to do R&D in grasping, manipulation, robotics technology, we are hiring at the moment, both in London and in Madrid. Our Spanish office is roughly doubling in size this year. We sell robots all over the world, and as you can see from the picture, we're best known for building hands for robots. We've sold these to all kinds of interesting people all over the planet. Of the pieces there, the most interesting one for this is the airline in the middle there, ANA. ANA approached us a couple of years ago to say, as an airline, we're trying to move out of just doing flights because we think that it's a very crowded market and it's very, very competitive, and we'd like to do something innovative and novel. And we said, okay, why are you talking to a robotics company? They said, well, because we want to do telepresence. We want to put people in distant locations and fully immerse them there, make it possible for them to feel like they're actually in the other place without having to travel there. Wow, we said, okay, that sounds like a really interesting challenge. And so we pulled together a few people we've been working with, and we put together some things we're calling tactile telerobots, for want of a better name, to try and address this challenge to make that happen. And some of the other customers there you'll be familiar with, people like OpenAI, MIT, NASA, Carnegie Mellon. SynTouch in the bottom left are particularly important to us because they're the people who make our sensor touch possible at the moment. I'll come back to that. So what did we put together? Well, working with SynTouch, who make touch sensors, and Haptex, who make haptic feedback gloves. This is the system that we had running in January last year in Tokyo. This is right in the heart of Tokyo in ANA's headquarters building. And on the right there, you can see Jeremy Fishel from SynTouch typing successfully. That's not the first time we managed to type remotely. At one point we did it and it just said help. Because he hasn't got any very good optical feedback at that point, but he can actually feel he's typing on the keyboard. And on the left, you can see Mike from Haptex giving a shoulder massage to Luke from Shadow, which we think that's probably the first time that was ever done with a robot, and we have now done that in a transatlantic kind of way as well, just for interest. But this is, from an engineering perspective, this is quite a simple system. It's just the Haptex gloves connected to a Vive tracker, connected to a UR10 arm and a Shadow hand. Obviously, each of those things is itself very complex, and there's some subtleties in how you get the whole thing to work and work well. But effectively, once we got those components to that level, it became quite easy to put this sort of system together. So yeah, we've run this from quite long distances. People ask us about latency and so on, and we say, well, from London to San Francisco with a 4G connection in San Francisco and our normal internet in London, we were getting around 160 milliseconds latency. And we had a bunch of journalists in the Wired office come up, put the glove on, and kind of play with blocks and cubes and sticks and balls in our London office. We had about half a second latency on the Zoom call that we were using for the remote vision. The really interesting thing there, of course, is if your vision lags your sense of touch, it's actually fine, because when you reach to touch something, you can feel the object before you can see that you've touched it. If your touch lags your vision, however, reaching for things is very difficult because the hand occludes the object just at the point when it gets critical to know exactly where it is. So that's that was the first point where we thought to ourselves, oh, actually, this touch is really giving us something important in terms of using a hand remotely and getting a human to be able to do that. So just to kind of go through the what we were doing system there, essentially we've got the robot hand on the left, the human intelligence at the top, and the sensing of touch at the right. The Haptex gloves at the top there, they give us the ability to render a sense of touch to the human. They have an array of inflatable pneumatic bladders on the fingertips that inflate and deflate, high frequency control of those, so you can create perceptual illusions of various types of touch and contact and so on. You can do very crude things like just inflating and deflating them to give a sort of an immediate contact, or you can do more subtle things where you vibrate them, oscillate them, respond dynamically to give a kind of more information. And we've been able to do things like render shear forces, sliding forces across the fingertip so that the wearer of the gloves can tell whether we're sliding to the left or the right across the fingertip, which is quite a subtle movement and quite impressive to be able to communicate that. The other thing the haptic system does is it tracks the fingertips of the hand. So we're not using optical tracking of the hands, we're using magnetic tracking. That's very precise and very accurate and gives us the ability to do some really fine movements there. You can't see it here, but we're using Vive motion trackers to track the coarse movements of the arm. Then on the biotax on the bottom right there, we have the sense of touch that's very, very important to getting the robot to be able to handle objects well. And we're using fairly normal cameras and audio setups. We haven't done anything special in terms of that yet. The shadow hand on the left, obviously a very high-end robot hand, 24 movements, 20 degrees of freedom, 4 under-actuated coupled joints, strain sensing on all tendons, so that's 40 strain sensors, position sensing all the joints and so on. That gives us a really good way to copy the human hand movement and embed that in the world. And so we kind of close the loop around this chain from the human intelligence through the actuator into the sensing, via the sensing at the remote end. You can see here a couple of examples of what's possible. I'll just leave this playing for a second. So this is basically what we were exploring last year with this system. We think this is about the most dexterous telerobot system in the world in terms of being able to perform simple tasks really, really easily and being able to perform complex tasks at all. So some of the things we're doing here with this telerobot are incredibly challenging, and we've never seen anybody do it with software systems at all. Even some of the reinforcement learning things that OpenAI have been doing address tiny parts of this and don't sort of address the full spectrum. And then there are things that are really hard to do even with this. Putting the cap on the bottle there is really subtle, and if your vision is occluded, is really, really hard even with a sense of touch. But we can even just about handwrite remotely. That's what we call medical grade handwriting. If you can read a doctor's writing, you can read what that's written. Otherwise, it's pretty much useless. But we'll get there. And as for the Rubik's Cube, unpacking it, taking it out of the container, taking it out of the package, that's actually really challenging. Twisting it and rotating it is surprisingly easy, although knowing what you need to do to get it to work is obviously the core challenge there. And the other thing that we're able to do with this is to handle objects that we can't quite see remotely. So again, that's a really important thing. Touch gives you the ability to deal with something where you can't tell what's going on. And here there's just reaching into a bag and taking an object out of the bag, and the operator has an occluded field of vision there. They know there's something in there, but they don't know what it is. Nice thing about using cobots is, of course, doing things like that is relatively easy. Your kind of risk management and risk assessment is feasible. And here's the kind of second intercontinental massage. And the flexibility of the movement here is really, really good. This is a level of kind of dexterity and agility that we were, even doing it, we were impressed by doing it. I wouldn't recommend doing this as your source of research funding, but we were in Vegas, so we figured that a little harmless pickpocketing was something we could probably get away with. One thing I don't know is whether we could actually feel Jeremy's pulse at the point when we were touching his neck. I think that might be just beyond the touch sensors yet, but it's an interesting direction to go in. So what does tactile sensing give us here? Well, the biotax that we're using are a well-known sensor in the research community. I won't spend too long on this because either you know about the biotax and you're familiar with them, or you don't know about them. But to be honest, it's a 10-year-old sensor. So there's probably better out there in the state of the art now. The practical point for us is that this is a sensor that I can simply send a purchase order to someone in California and a couple of weeks later get a sensor back that matches a spec sheet, that matches a functional spec, and has an interface that I know what it will be. And it has a reliability and a robustness that means I can then send that on to a customer and expect it to work. What the sensor does is almost secondary to that. For me, commercially, the ability to buy it is the key thing that makes a difference between this is an interesting R&D collaboration, let's see what we can do with this prototype sensor, and this is a real sensor I can tell other people about and make and ship. In the past, we have made prototype sensors of various sorts and let people use them and deploy them. And what you find out very quickly is that the sensor that works well in the research lab does not work in the long term when you send it halfway around the world to somebody who's going to hammer it into a table all day. And getting across the difference between a sensor that you can wire up to a rack of electronics in a lab and use and demonstrate marvelous behavior, and a sensor that you can integrate into a finger of a robot with basically no more electronics than you can see there in the top right hand picture. Getting that across is quite challenging for people who've just made an amazing new capacitive touch sensor that, as long as you can measure femtofarad results, it's absolutely perfect. So this sensor here is quite nice because it's a fusion of multiple techniques to do sensing. It has force sensing from this deformation of the skin. It does vibration sensing with a pressure transducer. And that means it can replicate some of the properties of the fingernails, of the skin surface that gives you the ability to understand slip and contact and movement. It has temperature sensing because it's a little bit warm. The temperature sensor means you can actually tell the characteristics of the material that you're contacting when you touch it by measuring the change in the drop in temperature at the point of contact. And you can see at the bottom there some results from SynTouch analyzing how different materials behave when you touch them. And in fact, SynTouch have demonstrated that they can pull out this sort of map of 16 or 17 characteristics of touch for an object and use that to quantify what the sensor is touching. And they now have a separate product line which consists of a touch sensor that's used for materials characterization that they sell to people doing such fantastic pieces of engineering as I'd really like to make a seat that feels like it's made of really, really expensive leather, but I don't want to use really, really expensive leather. Which of these plastic substitutes feels like that expensive leather? And using this kind of characterization analysis model, they've actually been able to successfully do those kind of discriminations. And so it's now used in high-end design to say, okay, how can we scientifically show that these materials are equivalent to the materials we wanted to use in terms of how the human feels them and understands them, which is pretty cool. Of course, the challenge that you then have as a teleoperations system designer is how do you take that complex set of data and turn that into something that the human at the other end of the system can understand. And that's still a technical challenge for us. If you have better ways of doing haptic rendering, I'm also interested in talking to you about those later on. So what does it do for robotics? Well, touch, very fundamentally for humans, it is what we use to connect with the world. We see things, but we don't believe they're there unless we touch them. That's a very, very important grounding for us. And the sense of touch, your ability to interact with objects, the way you interact with objects is a huge part of how you learn your motor movements, how you learn to interact with things, how you learn to operate in the world. Without a sense of touch, it's very hard to actually get vision to work. Vision bootstraps partly by touching things and moving things through the field of vision. So it's a really, really important kind of fundamental part of the way the brain works. We've done some slightly odd things with it. Just to show that you can go further than just operating random color blocks. This is a piece we did for Channel 4 where the comedian John Richardson had a date with his wife while he was in California and she was in London at the Vodafone offices. Apparently 5G made this possible, although I think that probably a large telerobot system and tactile sensing was the real underpinning of this. But he was actually really impressed that he could engage with his wife in a kind of what we call emotive way. And she was definitely like, well, I've actually had a date with my husband here, a slightly weird context and engagement of it, but it's not the worst date we've ever been on. I'm not completely sure about feeding people with a telerobot, but he managed it. So that's certainly something that we were very pleased was possible. So we're now looking at seeing what else we can do where you want fine dexterity, fine manipulation control to use these kind of robots for that. If you don't have touch on a robot, things break. Robots break cans, robots crush things, robots squeeze things and damage them. Robots that can't see things very well will end up impacting the objects, and if the objects are not sturdy, they will cause them some damage. Meanwhile, humans without vision, also without touch, you can see on the left there some research that was done. Again, I think it's in touch. So I think that's the Deco hand. But the person there, Jesse Sullivan, is an amputee who's using a prosthetic hand that doesn't have touch feedback, and he can do fine manipulation tasks. There he's picking up one of the plastic cups we were using earlier, but it requires an absolute sense of concentration from him. He's looking at it all the time. He's really, really concentrating. If you have a sense of touch, suddenly movement becomes fluid because you almost delegate picking things up to your sense of touch. You know where the object is roughly, you reach for it, you try and touch it, you feel it, it's there. And so that's what touch gives you on doing that. So here we see kind of working in constrained and unconstrained environments. The robot on the bottom there is obviously over-constraining the problem and can just use vision to solve it. The human at the top is using both vision and touch, although I suspect that from the start of there they could do that blindfolded. The robot is a lot faster than the human, but then the human could do that in a different place. In terms of what we can do with telerobots, we've seen a lot of really impressive telerobotic systems that don't use touch. We've seen people in the EOD, bomb disposal community, do really, really hard tasks with very, very simple telerobots, but they train all the time. They train constantly, and if they stop training, they lose the ability to do it. Whereas on the right there, any trillionaire can pick up this system and be using it in a matter of seconds. We gave Jeff about 10 seconds of briefing on how to operate it, and he just put the gloves on and was able to control the telerobot there. So where do we see these going in industry? Well, we're pretty simple people. We want to put these robots where humans shouldn't be. Difficult, dirty, and dangerous places. At the moment, on the left there, that's someone in an air-fed suit going into a very hostile environment, and they can typically do a 2 to 3 hour shift in there before they have to come out again. And it's dangerous and it's risky. If robots have more dexterity, then hopefully they'll be able to work in those spaces. So we want to do that. We want to put those robots pretty much anywhere and control them from anywhere else, whether those are dangerous and inaccessible environments, or whether that's just taking a skill and putting it in a different place, or exploiting autonomy and intelligence in the robot so that the human can control multiple robots, so that the robot can do a semi-automated task, and when it gets stuck, the human can reach in and use their vision and their touch and their intelligence to make the task possible. We think this is a really interesting kind of step change in what can be done, because now we can put a sense of touch anywhere, and hopefully we can understand how to use that to turn that into deployable skills, to turn that into effective telerobots. Once you can do that, then all sorts of things remotely become possible. Telerobots traditionally have had very, very simple grippers precisely because it was hard to control them. Now we can do hopefully tasks like the one on the right with the remote telerobot. So, sense of touch, absolutely important to get manipulation and perception to work well. You can do things with just vision, but touch makes them easy. If you're doing complicated tasks, difficult tasks, or stressful tasks, having a sense of touch makes it easier for you to do, makes it possible for the operator to get on and do the task rather than operate the machine, which we think is the real transition here. Using the sense of touch to make it easy for humans to use their innate understanding of touch to do tasks well. So our hardware is now out in the world and available. We can't give you the guy on the right, but we can show you robot systems. We've got some running in London, and we'll have some running in Madrid later in the year for those of you traveling from safer countries. And yeah, if you're interested in it, please do get in touch and talk to us about it. Thank you.